Hello friends, I am Ayushi Agarwal and I am an educator on Unacademy. You can follow me on Unacademy Learners app. Over there I have made 10 courses till now. First on digital electronics and then on control system. And in this lesson I'll be telling you about Routh-Hurwitz criteria and then I'll be discussing some few of the special cases of Routh-Hurwitz. You can follow us on YouTube channel and subscribe our channel. Let's start with control system. Before that, I would like to give my brief introduction about myself. I am a BTech graduate from Hindustan College of Science and Technology in Electronics and Communication Engineering with First Division Honours, and you can rate, review and recommend my videos among your friends. You can also follow me on this given link below. The target audience for this course is engineering students, all those who are pursuing their engineering. They can go through my courses since these are theoretical topics are going on, and these will be useful for you to understand, and so that in your examination you can easily attempt any question based on these types of topics. And all those who are preparing for GATE, they can also go through my courses since this is one of the most important topic Routh-Hurwitz, as every year question comes on this topic, and I have solved many previous year questions on this topic. You can also go through those questions. Weightage analysis, I have already discussed with you the last 12 years weightage analysis of control system. So in average you can take around 9 to 8 marks are going to come from control system in GATE examination. Routh-Hurwitz stability criteria. So this is one of the most important method to check whether the system is stable or not. The criteria is having one necessary condition and one sufficient condition for stability. So Routh-Hurwitz criteria has one necessary, that means one condition should be fulfilled, and the other condition one sufficient condition. If any control system doesn't satisfy the necessary condition, then we can say that control system is unstable. So the necessary condition which I will be discussing, if any of the system does not satisfy that condition, then we cannot call that system as a stable. It will be called as an unstable system. So basically we use this method to check whether the system is stable or unstable. One method to check is, like, we can find the roots, and then if all the roots of the system lies in the left hand side, then we can say that system is stable. But the main problem is this: as the power increases, so it becomes difficult for us to calculate the roots. Let's move forward. So what is the necessary condition? The necessary condition is that the coefficients of the characteristic polynomial should be positive. That means all the coefficients should be positive. It means all the roots of the characteristic equation should have negative real part. Suppose this is the characteristic equation of order n. So a0 s to the power n, a1 s to the power n minus 1, and so on is equal to 0. Over here these coefficients a0, a1, a2 and so on, these coefficients should be positive. So this is the necessary condition, the first and the most important condition which we have to check for Routh-Hurwitz stability is that all the coefficients of the characteristic equation are positive. If they are positive, then they should have real negative part. Now, there should not be any term missing in the nth order characteristic equation. That means if the maximum term is s to the power 3, then after s to the power 3 every term should be present, that is s to the power 2, s to the power 1, s and s to the power 0. This means that the nth order characteristic equation should not have any coefficient that is of 0 value. As I already told you, if the maximum power is s to the power 3, then after that there should be every coefficient. There should not be coefficient which is equal to 0. If the roots of the characteristic equation exist to the left half of the S-plane, then the control system is stable. As I have already told you, if the roots lie on the left half, then we say that the control system is stable. But if any one of the root lies in the right side, then the system is unstable. So basically, system is stable only when all the roots of that system, all the roots of that equation lies on the left hand side. If a single root also lies on the right side of the system, then the system is unstable. So this is the important condition for stability of a system. We have to find the roots, and to find the roots of a system, so it becomes difficult to find the roots for those equations as order increases. As I already told you, like we can find the stability if we find the roots of the system, and if we see that all the roots are lying on the left hand side, that means the system is stable. But as like there may be some equation whose power is s to the power 5 or s to the power 6, so at that condition it becomes very difficult to find all the 6 roots, since it gets quite complicated. So that is why, to overcome this problem, we use Routh-Array method. So this is the reason we use Routh-Array method. In this, we don't find root, we only find number of sign changes in the first column of the Routh table. So basically what we do is, we do not have to find number of roots. We are going to find that how many times the sign has changed in the first column of the Routh table. So we need to follow these steps to form the Routh table. The first step is, fill the first 2 rows of the Routh array with the coefficients of the characteristic polynomial. Start with s to the power n up to s to the power 0. That means in a characteristic equation we have s to the power n, that means the highest power of n to the s to the power 0. So all the coefficient of these power we need to write in the first 2 rows of Routh array. I'll tell you afterwards how we write these. Fill the remaining rows of the Routh array as mentioned in the table. If in a row there are elements with common factor, then you can divide the row elements. Like if they are common factors, then we can divide it so that our calculation becomes easier. Now, suppose this is our characteristic equation. You can see over here a naught s to the power n, a1, and moves on, and the power is decreasing one by one. So what we need to do is, we'll make a table. In that table, on the left hand side, we'll write s to the power n, that means the maximum power, and then decreasing one by one up to s to the power 0. Now we'll start writing the coefficients. For that, the first coefficient a0 will be written over here, then a1 will be here, then a2, a3, a4, a5. So if you notice, we'll follow this pattern. One first here, then here, here, here. So this sawtooth type of pattern is being followed, and like this we have to fill all the coefficients. Now from the third row we have to calculate. Now for this calculation, what we need to do is, b1, I've taken it as b1. b1 is equals to a1 into a2. We have to cross multiply each other. a1 into a2 minus a3 into a0 divided by a1, this column. For this, b2, a1 into a4 minus a5 into a0 divided by a1. So basically for this row, we will divide all the elements by this term. And for this row, if we consider for this row, c1 is equals to b1 into a3 minus b2 into a1, and we'll divide it by b1. And if we consider this term, it will be b1 into a5, b2, that b3 into a1 divided by b1. So for this row, all the elements will be divided by b1. So this is how, like when we'll solve some question on this, then only you will understand how we can do this, how this can be obtained. So this is very easy, but after solving question only you will understand it properly. So let's take an example. The characteristic equation is s to the power 4 3s cube plus 3s square plus 2s plus 1 equal to 0. Now this is the characteristic equation and we need to place the coefficient of this equation in the Routh array table. So coefficients are 1, 3, 3, 2 and 1. As I told you, we'll be placing it like this, in this manner. So 1, 3, 3, 2 and 1. Now how we can determine this term? 3 into 3 minus 2 into 1 divided by 3, therefore 7 by 3. For this term, 3 into 1 minus, if there is no term, we'll assume 0 over here, minus 1 into 0 divided by 3, therefore 1 will be the answer. Now for s to the power 1, this row, 7 by 3 into 2 minus 1 into 3 divided by 7 by 3. Therefore, we will get this answer. And similarly, we can do for this. And then for this also, we can perform the same calculation. Now, we can see that there is no sign change in the first column. This is the first column. This is 1 positive, 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 positive and positive. That means all the terms are positive. There is no sign change, which means that the system is stable. So this is how we can determine the stability of a system. Now there are two special conditions in Routh-Hurwitz's criteria. So we'll discuss those conditions in my next lesson. So thank you guys for watching my video and keep learning.